The ballistic pendulum problem is a really nice problem that encapsulates the idea of conservation of energy and conservation of momentum. In this problem, we have a large wooden block of mass 5.4 kilograms that is hanging by two strings, and we have a small bullet of mass 9.5 grams. And this bullet will approach the wooden block, which I drew in moment A. The bullet will burrow into the block, eventually becoming embedded in the wooden block. And at this point, the block is going to be moving with the bullet embedded inside it. And the block will swing up and reach a maximum height of 6.3 centimeters above what its previous height was. So we are asked to use this information to find the initial speed of the bullet. For this problem, we are going to employ energy conservation, we are going to employ momentum conservation, but we are going to need to be careful which of these conservation laws we actually use. So the first conservation law we're going to use is energy conservation. I know that between moment B and moment C, energy is going to be conserved. There is some amount of kinetic and potential energy at moment B, and there is some amount of kinetic and potential energy at moment C. So to find the total energy conserved, we could write out the kinetic energy at moment B, the gravitational potential energy at moment B, and then we could write out the kinetic and gravitational potential energy at moment C. So we want to connect moments A, B, and C together. We are ultimately trying to find the speed of the bullet at moment A, the speed of the bullet before it actually hits the block. How should we connect these moments? In other words, which conservation law should we use? And which moment should we try to connect first? We could try to connect moment A to C, moment B to C, or moment A to C. So first of all, I'll say pause the video, think about which moments you want to connect first, and then start the video when you have your answer. We are going to try to connect moment B to moment C first. Now, why did I make that choice? Technically, I don't know the best way to solve this problem right now, but one clue was that the question asked me to find something about what's going on in moment A. If this is ultimately what I'm trying to find in this question, then I'm probably going to need to connect moment A to another time last. So let's forget about moment A for the moment. Let's try to connect moment B to moment C. So again, pause the video, think about, should we use energy conservation or should we use momentum conservation to connect what's going on at moment B to what's going on at moment C? So which should we use? Energy conservation or momentum conservation? Well, we're going to use energy conservation to connect moment B to moment C. What is my argument for that? At moment B, the bullet has just embedded itself in the block. The bullet hit the block, it burrowed in, it got stuck in the block, and because the bullet hit the block, gave it a kick, the bullet and the block together are swinging to the right. Now, the bullet just embedded in the block a split second ago. A fraction of a second ago, the bullet had not yet hit the block. The block did not really have a chance to begin rising up in a substantial way. So to a good approximation, I could say the bullet and the block are moving entirely to the right. And they are moving to the right with some speed that I'm going to call VB. In moment C, the bullet and the block are traveling together. They were hit in moment B, but they swung upward, and at moment C, they reached their high point. When the bullet and the block reaches their high point, they're going to temporarily stop before swinging back down. Well, when they reach their high point, the speed of the bullet and the block, which I'll call VC, is going to be 0. I also noticed that at this moment, moment B, the bullet and the block did not rise up any above their initial height. So I could say they're still at their initial height. I'll call that YB is equal to 0. At this moment, the bullet and the block did rise up by an amount 6.3 centimeters. So I could say they rose up by 0.063 meters. We converted centimeters to meters. So I could say at this moment, YC is equal to 0.063 meters. If I look at this problem, look, this looks very similar to a pendulum. Moment B is when the bob of the pendulum is at its low point and moving at its fastest speed. Moment C is the pendulum when it reaches its highest point. So we're going to use energy conservation to match moment B to moment C. So I could write this as the total energy at moment B is equal to the total energy at moment C. Total energy is going to be composed of kinetic energy and gravitational potential energy. So I could write kinetic energy at moment B is going to be 1/2 times the mass of the things that are moving. Because the bullet and the block are stuck together, they are moving together, I could treat them as one single mass of mass 5.4 kilograms plus 9.5 grams. Just to make my writing a little bit easier right now, I'll just write that as M bullet plus M block. So I have M bullet plus M block times the speed at which they're moving squared, which is VB. So VB squared. The potential energy due to gravity at moment B, I could write as mgy. So the mass of the thing that I'm looking at is the bullet plus the block stuck together. So mass bullet plus mass block times g, acceleration due to gravity, which is 9.8, times the height of these objects at this moment. We said the height is 0. So then the potential energy due to gravity ends up just being equal to 0. So I could say this term is equal to 0. Similarly, I could look at the energy at moment C. Kinetic energy at moment C is going to be 1/2 times the mass of the objects, mass bullet plus mass block, times the speed at which they're moving at this moment, squared. The speed squared is going to be 0, so times 0 squared. So the kinetic energy at this moment is 0, and I could say that the potential energy due to gravity at moment C is going to be mgy. So mass of the bullet plus mass of the block times 9.8 times the height, which is 0.063, 0.063 meter. Now, from energy conservation, the sum of these two terms, which is basically kinetic energy plus 0, because we're multiplying by 0 there, is equal to the sum of these two terms, which very conveniently for us is going to be this term plus 0 because we have a 0 there. I'm not actually canceling out the masses in these terms. I'm just setting this entire term equal to 0. So now we're going to use energy conservation to solve for the speed of the bullet and the block moving off together at moment B. So I could say that the kinetic energy at moment B plus the potential energy at moment B is equal to the kinetic energy at moment C plus the potential energy at moment C. Now, before I actually plug in numbers, remember the kinetic energy at moment C we said is 0, so I could get rid of this term because it's 0. And the potential energy at moment B I could also get rid of because that we said is equal to 0. So the kinetic energy at moment B is 1/2 times the mass of the bullet and the block together, mass bullet plus mass block, times the speed at which these objects are moving squared, plus 0 equals 0, plus the potential energy at moment C, which is the mass of the bullet plus the mass of the block, because they are again traveling together, times 9.8 times 0.063, which is their height at moment C. Now, if I wanted to, I could plug in 5.4 kilograms for the mass of the block and 0.0095 kilogram for the mass of the bullet. Remember, we should be working in kilograms, so I would need to do a conversion. But I noticed that I have the total mass of the objects here and the total mass of the objects here. So instead of worrying about their masses, at least in this particular equation, I could just cancel the masses out. And when I do that, I find that I'm left with 1/2 VB squared is equal to 9.8 times 0.063. And if I go through the arithmetic of it, I find the speed of the bullet and the block together, which is the speed of these objects at moment B, is given as 1.11 meter per second. Before we go on and connect moment A to moment B in this problem, I want to take a second to discuss why we chose energy conservation to connect moments B and C together. Could we have used momentum conservation? The answer to that is not really. And here's an argument for that. Momentum as a quantity is given as P equals mv. In moment B, we have 4 objects. We have the bullet, the block, and the 2 strings that are tied to the block. If we assume the strings are massless, we could effectively ignore them in this problem. In moment B, the bullet and the block are moving, so the bullet and the block will have some velocity, and therefore they will have some momentum. In moment C, everything has come to a rest. So in moment C, I could look right away at this equation, say if everything is at rest, the momentum at moment C is going to be 0. But at moment B, these objects are moving, they will have a non-zero velocity, and the momentum will be something that's non-zero. So here the momentum is 0, here the momentum is non-zero. Does that mean momentum is actually not conserved? Well, not really. The thing is, the block is attached to a string, which is attached to the ceiling, which is attached to a house, which is attached to the earth. And as a result of the block being struck by a bullet and swinging up, the earth itself is going to move ever so slightly, and momentum would still be conserved. But the thing is, to properly employ momentum conservation to connect moments B and C together, we would need to account for that movement of the earth, however small it would be, and that would just be way too hard to track for a problem like this when we can just look at energy conservation. So how do we connect moments A and B? Do we use energy conservation or do we use momentum conservation? Pause the video, think about it, and come back with an answer. To connect moment A and moment B in this problem, we are going to make use of the idea of momentum conservation. Why did I choose momentum conservation instead of energy conservation? Strictly speaking, both of these quantities are going to be conserved. But the thing is, keeping track of energy conservation is going to be very difficult, while keeping track of momentum conservation will be relatively easy to do. Why is energy conservation so difficult to keep track of in a problem like this? Well, before the bullet strikes the block, we have a block and we have a bullet, and the bullet will have some amount of kinetic energy. And we could say, okay, the total energy is the kinetic energy of the bullet. We'll say both the bullet and the block have a height of 0, so we could ignore potential energy. After the bullet strikes the block did not really rise up in any significant amount, so the potential energy did not change. But think about what it took for the bullet to burrow into the block. The bullet needed to break some of the fibers in the wood, and the bullet would rub against the wood as is burrowing into the block and heating up due to friction, eventually coming to a stop. How do I keep track of the energy needed for breaking those wood fibers and increasing the thermal energy of the wood and the bullet? That would be a very difficult problem to keep track of. However, keeping track of momentum conservation from moment A to moment B would be easy. This is just a momentum conservation problem in one dimension. So I'm going to use momentum conservation. The total momentum, the momentum of every object at moment A, is equal to the total momentum, the momentum of every object at moment B. Because momentum is a vector quantity, we should be assigning a positive and a negative direction. So I am going to choose to the right is the positive x direction, to the left is the negative x direction. When we say total momentum at moment A, we mean the momentum of every object in our system. In this system, we have two objects that we care about, the bullet and the block. So the total momentum at moment A, P total A, will be the momentum of the bullet plus the momentum of the block. At moment A, the bullet will have a mass of 9.5 grams. We should convert that 9.5 gram to kilogram. So the mass of the bullet is 0.0095 kilogram. And the velocity of the bullet is what we're trying to find. The bullet is moving in the positive x direction, so I'll write the velocity of the bullet as positive VA. And I need to add the momentum of the bullet to the momentum of the block. The block in moment A has a velocity of 0. So I would formally write the momentum of the block as the block's mass, 5.4 kilograms, but I multiply that by 0, so it will end up falling out anyway. So I find the total momentum at moment A is 0.0095 VA. Now let's find the total momentum of the bullet and the block at moment B. So I could say the total momentum at moment B is equal to the momentum of the bullet at moment B plus the momentum of the block at moment B. So the momentum of the bullet would be the bullet's mass in kilograms times the bullet's velocity plus the mass of the block times the block's velocity. We will assume to a very good approximation that the mass of the block did not significantly change. The block was burned a little bit, there were a few wood fibers broken, but we'll assume the mass did not really change, so the mass is still 5.4 kilogram, and the block is moving also with a velocity of 1.11 meter per second in the positive x direction. If I wanted to, I could have combined these two masses together and written them as a single, more massive object moving with that same velocity. That would be a perfectly okay way to solve this problem as well. When I set the total momentum at moment A equal to the total momentum at moment B, I would get total momentum at moment A is 0.0095 VA, and the total momentum at moment B is this. So I have 0.0095 times 1.11 plus 5.4 times 1.11. So I put these in a calculator and I find VA is equal to 632 meter per second.